This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
Hello, last lecture tonight, lecture number 17. So everything that you still need to know about these NURBS curves and NURBS surfaces, right? I will cover in one lecture. Is that possible? Well, I try my best. So let's go into the non-uniform rational B-spline surfaces directly with an example. Okay. So where did we stop last time? I think last time I had an illustration on the board and started to do an example to evaluate a particular NURBS surface. And let's do that again. So I put a control mesh on the board, and here we go. A bunch of happy points and happy line segments defining this mesh. And the control points are called the Bohr points, Dij. In this particular example, the lower left point is called D00. The right point here is D30. The upper right point is D33. And this point would be D03. What else do we need? For this particular example, we need to look into the domain. And the domain of a surface has to be a two-dimensional region in the parameter space, and the parameter space is a UV plane. I have to specify orders and say, in this particular example, I say that the orders K and L are both 3. A B-spline surface has 2 orders, one for the U and one for the V direction, and they do not have to be the same Sohail, right? They can be different. And so what else? We have control points, we have orders, we need these not vectors. And so if I have this setting, 4 times 4 control points, and orders being 3 and 3, then I'm talking about a particular biquadratic B-spline. This is biquadratic B-spline surface, B-spline surf. Okay. And I need 2 not vectors for U. I need 2 relevant domain intervals here, 2 knots to the left, 2 knots to the right. And I need for the V direction also 2 domain intervals, and 2 to the left and 2 to the right. I do the numbering. The numbering is U0, U1, U2, U3, U4, U5, U6, and the V knots are called V0, V1, V2, V3, V4, V5, and V6. And here's the domain portion in V. Here's the domain portion in U. What is the domain of the surface that is not yet visible under the control mesh? The domain will be the Cartesian product of the relevant domain portions of these 2 intervals. This is it, right? So if you take this part of the real line, the U line, and this part of the real V line, the Cartesian product will be this particular region here. Meaning there will be 4 segments or 4 patches defined by this control mesh. Okay, so what is the formal definition? The formal definition of such a surface, a B-spline surface, is S depends on U and V parameters, and it's a double sum, I from 0 to M, and J from 0 to N of control points called Di, J, multiplied by the B-spline basis functions Ni of order K, U, times Nj of order L, depending on V. Okay. All right. So what is the data I have? The data are the 2 not vectors, the control points, and the implied control mesh, the 2 orders. And now I would like to evaluate. That's always the problem. And I say we want to utilize the entire B-spline machinery as we have developed it. And we would like to use the entire set of tools that we have already coded up and do what we know how to do for curves. Where are the curves? We already talked about the Bezier surfaces, where you essentially can treat such a mesh row by row or column by column and treat the individual polygons in this mesh as if they were control polygons of curves, right? You remember that? If we adopt the same viewpoint, we have to see the curves somewhere in this formula, and we have to see the control information for curves somewhere in this control mesh. All right? The trick is this. Again, you look at this expression in the formula, and you call that an intermediate point. You just declare this as an intermediate control point, dj, which depends on u. Okay, so then you are just left with sum j from 0 to n of dju control points times njl of v. What does this mean? What am I doing there? I'm saying, look at the inner part of this double sum, this part, and when you look at just that part, that looks like a curve, right? It's a sum, it's a point, it's a basis function. That's a curve. So what comes out of this evaluation is some point, this point. And then you again have only some point basis function. So that's again the structure for a curve evaluation. Now let me be concrete and talk about the evaluation for this particular value. Say you want to evaluate the surface for this location at, say, u bar, and here is a particular v value, v bar, for which you would like to evaluate. Okay, so where's this point, this parameter tuple that you want to evaluate for? The parameter tuple is here, right? You want to evaluate there. What is the corresponding point xyz on the surface for the parameter tuple u bar, v bar, right? Compute the surface point S for u bar, v bar. Okay. How do we do that? Well, we apply n plus 1 times this curve evaluation scheme. But really, n plus 1 times, isn't this a local scheme? Isn't a B-spline something local? Indeed it is. And we do not have to consider all the control information, right? What do we have to consider? We have to consider the following. We have to look in the domain and see with what patch we are dealing with. We are dealing with what patch? For a B-spline curve, we had a bunch of segments making up the curve. For a surface, we have a bunch of surface segments or patches making up the surface. All right? Meaning, this part here is the domain for the first patch, or one part of the surface. This part is another part for a second patch of the entire surface. Here is another part that defines a third patch. And this happy tuple, u bar, v bar, ends up lying in this particular rectangle in the UV space, meaning that we have to consider only the corresponding control points for that. So, again, think about patterns. If we are dealing with order k equals L equals 3, that means that each patch, this is the B-spline setting, each patch will be defined by 3 times 3 control points. For a curve, it meant that k equals 3, 3 control points define a segment. Now, each patch will be defined by 3 times 3 control points. If I'm dealing with a tuple in this upper right, the upper right domain rectangle, then it means that the corresponding patch will be defined by the upper right portion of the control mesh. So the particular portion of the overall surface for which I will compute a point will indeed be defined by these 9 control points, these upper right control points, if I may call them that. These are the control points that I'm dealing with. The rest is irrelevant. Again, local evaluation, right? Local property. Now, I evaluate 3 times in U direction. I compute these dj of u's by considering the dij's in this sub-mesh with these bulleted, or with these boldface control squares, and evaluate in u direction. So now I evaluate these 3 polygons, first polygon, second polygon, third polygon, for this particular u bar value. When I do that, you remember we had to do this mapping of configurations onto the line segments of the corresponding control polygon pieces. In step 1, we considered these ratios, and in a step 2, we considered that ratio. This is a configuration we have to apply 3 times to do 3 times a u direction evaluation step. Okay, so I just keep this configuration in my mind roughly and then apply it. So meaning I get this point, I get this point, I get the configuration here, I get the configuration there. Here is that configuration, there is that configuration, right? 2 points always connected by a new line segment. These are these intermediate line segments. And then I perform the second step, step 2, and get my circle kind of like in the middle. So, and then the middle point lies here, the middle point lies there, and the middle point lies there. Okay, so now I have these intermediate points, and those are these DJs. And so this guy then would be called, this is D1 of this particular u bar value. And this guy here, that circle would be D, what is it? 1, 0, 1, 2, 3. This is D3 of that particular, at that particular u bar value. Now what I do? Now I do the evaluation in v direction. I take these intermediate points, connect them, and evaluate in the transversal direction, namely the v direction, meaning I have to connect my intermediate points. Okay. And what do I do with them? Well, I also want to give this guy its name. That one was D2 of u bar. And now I evaluate for this particular v bar. Again, it's the same configuration, so have to consider this configuration here, and then I have to consider this, That was the first step. And in the second step, I only have to consider this guy, right there. Second step. So I have to map these configurations in v direction here. So I only have to do it once. So here is this intermediate point, that intermediate point. One last step, and then there is the happy point that I need that lies on the surface itself. Here is that point. There is my surface point S of u bar, v bar. And I'm done. Okay. So again, what is the message to take home here? The message is, if you understand B-spline curves, you understand B-spline surfaces. If you have implemented the entire toolbox for B-spline curves, you pretty much have everything in place for B-spline surfaces. You only have to apply all the algorithms essentially twice, in the u direction and the v direction. That's it. And here we go. That explains pretty much everything there is to understand here. In terms of the patches, again, let me come back to the patch configuration. I said for that control mesh there would be 4 patches, right? Yes, and let me sketch that again. So if you have this particular control mesh, 4 by 4 control points for a biquadratic B-spline surface, there will be 4 patches. And in this case, they would look somewhat like this. Okay, here are the control points, the happy squares. $16 of them. Okay. And there are the 4 patches, right? Patch number 1, patch number 2, patch number 3, and patch number 4. one surface, 4 patches, and each patch controlled by a local array of always 9, 9, 9, 9 control points. Very nice. Meaning, if you were to pull this control point up or down, it would influence only this upper right portion of the entire surface. That's it. Very cool. So that is the world of the B-spline surface. So then we can also do the actual, so that was actually NURBS, right, that I talked about? No, that was the world of non-uniform B-splines. I talked about NURBS, right? NURBS, non-uniform B-splines. So now I talk about the rational part, right? Now I talk actually about NURBS. Now comes the rational part, dividing things. So now I really talk about the rational setting. Rational setting. What changes? The only thing that changes is the fact that we have weights. So in this setting, we have the control points still di, j, right? I from 0 to m and j from 0 to n. Plus we have weights. We have weights, positive weights or zero weights, wij, I from 0 to m and j from 0 to n. So here we have the de Boer points. De Boer points, PNTS. We have the weights, non-negative weights. And we have orders, K and L, orders K and L. And we have two knot sequences. So one for U0 smaller equal, blah, blah, blah. Last one is U sub M plus K. And the second knot sequence is for V0 smaller equal, blah, 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 smaller equal Vn plus L. Okay, that's what we have. And we need the formal definition. We have the definition, def what is the rational B-spline. So I know I'm going fast here. S of uv is defined by a ratio. And we essentially take all of our control points, I from 0 to m, j from 0 to n, and we multiply the control points by the weights, weight ij times the control point, dij, times the basis functions, ni k of u times nj l of v. And we divide by the sum of all weights, in a sense. So we have to divide by sum I from 0 to m, j from 0 to n of all the weights, wij, multiplied by the basis functions nik of u times njl of v. Okay, that is the formal definition of the most general geometrical representation that we are seeing in this class, right? This is the most general creature we are dealing with. But we mustn't divide by 0, so we also have to say and condition 1, let's assume that all the weights, weight ij, are all greater or equal 0. And second, also that we do not divide by 0, meaning that sum over all I, all j of the weights, weight ij times ni k of u times njl of v is greater than 0. Okay, those conditions better be met. That is the most general geometrical primitive we are operating on. And again, I said the B-spline machinery goes back to the B-spline curve machinery, right? B-spline surfaces, all the algorithms and so forth, you can go back to your B-spline curve algorithms. And now we also would like to see how we can use our B-spline surface algorithms for dealing with rational B-spline surface algorithms. Okay, can we do that? Yes, there's this trick of embedding such a rational surface into 4D space. And I shall talk about that next, how we do that. You have seen this trick now multiple times. The trick is you use the weight as an additional dimension. So the control points for the surface are already 3 dimensions, x, y, z. The weight is the 4th dimension. And in order to do this embedding properly in the spirit of projective geometry, you multiply the first 3 spatial coordinates, x, y, z, by the weight. So, but, well, it's not a but it's very nice. But can map NURBS surface to 4D space. I should be more precise what this means, but I can't today. So I just say what it means. Meaning 3 steps are needed to do that. 3 steps are needed to do this embedding. Steps needed. And step number 1 is, again, you have seen this before. Step number 1 constructs these higher dimensional control points. This is map to 4D space. Okay, so we take the original de Boer point. The original de Boer point dij has coordinates x, y, and z with subscript ij, ij, and ij. And we have weights, weight ij. And these we map to 4D space by just constructing a new control point, dij star, and the star indicates this embedding into a space 1 dimension higher, which has 4 coordinates, weight ij, multiplying the x component, weight ij, multiplying the x component, xij, weight ij multiplying the y component, weight ij multiplying the z component, zij, and then the weight component itself defining the 4th coordinate. Now we can use these dij star control points and evaluate a B-spline surface in 4D space. So 2, we evaluate in 4D space. Okay. What do I mean? Now we are actually dealing with a surface point as also star for 4-dimensional, and we want to compute points on this surface based on the parameter uv. And now the definition of a point on this surface, no longer rational, but it's just polynomial in 4D space, looks like this. It's I from 0 to m, j from 0 to n, and now it looks like a standard B-spline surface, dij star, which has 4 components, namely those 4 components, multiplied by the basis functions nik of u times njl of v. And that is this important embedding step. But this is not the point that we want in the end. Okay, so this point has 3 components, of course. This point has an x star component, x star of uv. It has a component x star of uv, a component y star of uv, a component z star of uv, and the weight component, weight, no star here, weight of uv, which is not the point that we can render because it lives in four-dimensional space. So now the third step then is that we take one of these four-dimensional creatures and map it back or project it back to 3 space. That's where we make our pictures. So I just call it map to 3D space, or call it project to 3D space. Project to 3D space. And that's actually the surface point we want. The surface point, the ultimate surface point, S of uv, has 3 components, x of uv, y of uv, and z of uv. And they are related to these 4 coordinates in what way? Well, you divide the first 3 by the weight. So the first one is x star of uv divided by the weight of uv. The y star component of uv divided by the weight uv. And the z star component of uv divided by the weight of uv. And that's the result. So again, why do I put this on the board? I only put this on the board to tell you it's possible to use still all your standard B-spline surface machinery for even a rational B-spline surface. And for a B-spline surface, you can use all your B-spline curve machinery, right? So it's all related. You just have to do a few additional steps. And yes, here you have this division again. Finally, you have to divide, of course, and you have to make sure again that this way the weight component is not 0. All right, so far, so good. Now we have talked about all these different ways to represent geometry. Now we know how to represent everything, right? Now we know how to write a computer-aided design system. Can we do it now? Now we can work for a car manufacturer, right? Or for a design firm in Orange County or whatever, industrial design firm, and we can write a computer-aided design system, right? Yes or no? Well, that's the next course, right? The next course, Advanced Geometric Modeling, is about, okay, now we know about all these ways to describe and represent geometry. We know how to evaluate and degree elevate and insert knots and all of that. But now the real system design, system engineering, software engineering actually starts, right? You know, I mean, how to build a library consisting of 112 functions, right? For Bezier, B-spline, and rational B-spline curves and surfaces. Once you have that huge library, well then, on top of that, you have to then develop an interface library, right? You want to manipulate these things and create these things very effectively, and you have to worry about the entire database system, right? Obviously, when you design a car body, that thing will consist of thousands and thousands of those patches and surfaces. How to do that? Can't talk about that in this class. But I want to give you at least a flavor of some of the most basic and most primitive operations, how we can design simple geometry based on these representations. So there are some very standard operations to create surfaces. You know how to create curves, right? You have done that. You clicked on a bunch of points, and then these points were interpolated, and the resulting interpolating polynomial you represented in Bezier form, and you had the Bezier points coming out. So you know how to create a curve. How do we create a surface? Okay. The representations, the Bezier points or the B-spline, the Bohr points, the representation should be transparent to designer. In general, you do not want to think in those terms. You want to think only in terms of the geometry. Forget about these Bezier and B-spline control points. You only want to operate on curves and surfaces directly. So, what does this mean? One important surface creation scheme is the following. I specify a curve, and I say take this curve and extrude it, extrusion, okay, extruded by a particular vector. I specify a curve in 3 space. This is happening in x, y, z space. I specify a curve and then extrude it, pull it along some kind of line for a certain amount of distance. So if I extrude this by this particular vector, that means I take every point on this curve and want to move it to a corresponding point. That is, okay, this is standard surface operation scheme. Take a curve and extrude the curve where the extrusion is specified by that vector. So every point here on this first curve point has a corresponding point here, which is P bar, which is the point P plus this extrusion vector V, right? So this is extrusion vector V. Very simple operation. How do we do that? Okay, now we worry about the representation. Let's say our curve representation is a Bezier representation. So this curve would be given by a bunch of control points, defining a Bezier control polygon. And then, well, here at the polygon, there's another polygon right here. And then, but then I have to think in terms of a surface, so I have to connect these things, right? So from a curve to another curve, and then connecting the control points in such a way that now I have a control mesh that defines the underlying surface that I want. How do I do that? So a very simple and powerful surface creation methods, okay? Surface creation methods. So these are all very standard ways used in computer-aided design systems. And the first one I will talk about is a ruled surface, or an extruded surface. Extruded surface. Okay. Everything will be very simple. So here is my x, y, z. Now I assume that the underlying representation I have is a Bezier representation. So I have a control polygon with happy circles as control points, defining a particular curve. This is happening in 3-dimensional space now, right? We want to create surfaces. So then I call this first point B0. I call this last point BM. And I will worry about, say, a surface defined over 0, 1 in U and 0, 1 in V. So I want to define it over a unit square. And I have this vector that I need to specify, but first I need to say what this curve is. This curve is just a Bezier curve. Bezier curve C of U is a standard Bezier curve I from 0 to M of Bezier points Bi times Bi M of U, right? That's the representation for that curve in Bezier form. And now I want to extrude the curve in the direction or according to some specified vector. Okay? And it's very nice to just show I only have to take the Bezier points and I have to extrude the Bezier points according to that vector. That's all I need to do to get the polygon for the extruded curve. Okay, so I only need to extrude all these control points of the first curve. I extrude those to get these control points. Okay. So, and I have this extrusion vector here, right? This is this vector. I call it vector V. And I extrude each of the original control points, defining this new set of control points. And of course, that polygon there will define that curve. But I don't want two curves, I want a surface, right? So what does it mean? When I have a curve and another curve and I want to have a surface in between, I need to connect. And the way I connect in the simplest way is by linear interpolation. So the other way to connect then is, well, to connect these corresponding points by lines. Okay. So from a curve and its control definition to another curve and then connecting in the transversal V direction. What did I do? I need the following, right? I need the surface definition. The surface of uv is a Bezier surface, and I need the control points in I direction or u direction, which is I from 0 to m, and j. How many control points do we have in j direction? Only 2. Huh? Per control point and corresponding one. Huh? That is just translated by this translation vector. J from 0 to 1. Right? J from 0 to 1. Okay, and then I have control points that are interpreted as a two-dimensional array now, Bij, and it's Bi m of u, and it has to be Bj1. It's linear interpolation in V. Okay, but I need to know what are the Bij's. These are the Bij's, these points. Where what? This guy, obviously, B0 is B00, right? This guy, obviously, is BM0. And this guy, obviously, is BM1. This guy, obviously, is B01, and so forth. So I can say where B, I, 0 are the original control points that are specified, B0, B1, Bi, and so forth. Bi0 is the original control point, Bi, and Bi, 1 is Bi plus the exclusion vector V. That's it. Okay. What does the user specify to do this? The user specifies the control points for one curve and the exclusion vector. That's it. So the user specifies this initial curve, C of u, specifies C of u, and the exclusion vector V. That's it. Okay. Very simple, powerful, often required surface construction scheme. Now comes the next surface. And the next general surface is one where these two boundary curves, the first and the second, are not the same, but they are different curves. Okay? Here I copy the original curve, right? Just translated. First curve, second curve. These curves are the same, just translated versions of one another. Now I come to the next general case. A first curve and a second curve, they are different curves, and I want to blend a surface in between. That is called ruling. If I do the connection via line segments. So the next surface will be slightly different. Ultimately, you can think yourselves about what type of operators you want to take all these curves and build surfaces from it. Right? If you are faced with the problem of designing the functionality of a system that should allow you to design all the creatures in Toy Story or so, well, sooner or later you will come up with a bunch of required surface construction algorithms that you need. These are some of those. Next one is a ruled surface. A ruled surface. How do we do that? First, again, let's forget about the Bezier points and let's just talk about the principle of constructing a ruled surface. Forget about the representation. So I specify a first curve and I specify a second curve. Two curves, but it's empty space in between. Please fill in the space. How do you do it? Well, by line segments, right? I always say line segments. So you can have a point connected and you connect a bunch of corresponding points. The correspondence is based on the same parameter value, right? Same u. So this is the way you can do this here, right? This is called ruled surface. So here you have u, here is u, right? And here you have the v direction, right? You specify two curves, curve 1, C1, curve 1, and curve 2, and in between you connect corresponding points by straight lines. Okay. I described it without considering the particular Bezier representation. So now we give attention to that, and we look into the construction of such surfaces in the context of a Bezier representation. Again, x by z. But I want to show a different example first. Different example just to make this clear. Right? I can have, say, a shape like this, and I can have a shape like this there. And I can connect these two curves, right? Based on correspondences. First point goes to first point here. Last point goes to last point there. Point at 1/2 goes to point at 1/2. Point at 1/4 goes to point at 1/4. Point at 3/4 goes to point at 3/4, right? So you see how these correspondences allow you to really design much more general curves, much more general surfaces like that. Okay, so how to do that? So here the user would specify two curves, and in the Bezier world, these curves would be specified by their control polygons, of course. First curve, and I call it C1 of u, or C of u, which is a sum I from 0 to m bi's times bi m of u. And so this first point would be B0, the last control point would be Bm. And then the user would specify a second control polygon. Okay, like that. B0, B1, B2, B3 bar. So I would call this B0 bar, B1 bar, and B2 bar, and B3 bar. And so there is a second curve there, and the second curve would look like this. Right, that's the second curve, and I can give that a name of, I call it C bar of u, which would be sum I from 0 to m of bi bars, bi bar times bi m of u. Okay, that's the second curve. And now I want to connect with line segments. Connecting by line segments in the control mesh world means simply connecting the corresponding control points. Okay, that's all you do. So you take the connectors of these corresponding control point pairs, connect like that, and that's the control mesh for the surface in between. So what is going on? What does the user specify here? User specifies two curves, right? Specifies two curves, i.e. Curve 1, or the curve of u, and curve bar of u, curve bar of u. That's what's the input to this scheme. And what comes out, the output is the control mesh definition for this surface. So you get the Bezier surface S of uv, which is double sum, I goes from 0 to m in j. It's a ruled surface, meaning we just use as rulings straight lines, linear interpolation. Bij times Bernstein polynomials Bim of u times bj1 of v. Okay, that's it. And now I need to say where these bij's come from the original control points. Well, they are the same. They just have to go from a single index to a double index. Okay, that's the only issue here. So I just say where the bi, 0 is the original bi, and where bi, 1 is one of those bi bars. That's how I get the control mesh points from the control polygon points. And again, here I would assume that the whole thing is defined over 0, 1, 0, 1 for the u and v square, parameter square. So here in this case, I would have a nice gradual change from a convex shape to a shape with an inflection point, right? Along this line, I would have a linear change from this type of a curve to that cubic curve. So if I sketch this out, what this render that, then it would look like this, right? Okay. You get the idea. So that is a ruled surface. What other types of surface constructions can you think of? Yes, rotational surfaces. You are reading my mind tonight. Right? Rotational surfaces are probably very important. Probably the most important, right? Because everything is rotationally symmetric even, right? Doing rotations and constructing surfaces by defining one curve, defining an axis, and rotating that curve around that axis is an absolutely essential surface creation, surface construction scheme. And I think I can talk about that a little bit. So that was ruled surfaces, rational settings, rotational surfaces. What do we need to understand before we come to rotational surfaces? Rotations, a rational scheme. Did I talk? I only use Bezier stuff here, right? With rotational surfaces, are we leaving this nice world of polynomial things? We probably do, right? There was a reason, right? Didn't I say why we actually needed those rational things to begin with? To represent stuff, for example, that has to be precise and exact in a rotational setting, right? Rotation requires you to represent exactly what geometry? Rotation implies a circle, right? Right? Rotation implies circle. And circle implies weights, rational setting, to represent the circular arc precisely. So I didn't really talk about that specific geometry, the circle, or how to represent exactly a piece of a circle. Now we need it. So I will talk about it, right? A circle. Did you read the book about the circle? You know how to represent the circle? You know? How do you get a quarter circle? How do you do that? What are the basic control points for that and the weights? Know that?
You could do a triangle or do an actual square.
You do a rational, you have a triangle? Okay.
You just, you would actually need, 3 different curves.
I need 3 curves? Oh, you are talking about representing an entire circle.
Yeah.
Okay. So you have you have here a circular arc here. You have a circular arc here. And you have a circular, you have the control points, right? Arc 1, arc 2, arc 3, 3 arcs to one circle. I'm thinking? Okay. Good. I'm not there yet. I'm just thinking about how do you represent a circular arc, a piece of a circle? Okay, how do we do that? Next one will be the rotational, right? So note, we need to represent circles. Note, exact represent of a circular arc, right? If we know how to represent a circular arc, we know how to represent the entire circle of a circular arc. Okay. And now, after much derivation and conditions in algebra, at the end of the day, you get the condition. You can represent it with use rational Bezier curve. Bezier curve. Okay. And I give you the answer. Okay. B0, B1, 2. B0, B1, B2. And you want the curve that is implied by this polygon and the weights, which I haven't put on the board yet, to be a circle, a piece of a circle. Okay, so this thing should be a part of a circle. A circle goes on. In that case, you need to know the weights, because if you don't use weights, then this is just a parabola, right? It's not the circle. So I say the weight here, weight 0 is 1. I say weight 2 is 1. And now, when you actually do the math and the algebra, you will find that you have to consider an angle. You have to consider this angle here. I call this angle alpha. And the weight for this middle control point has to be the cosine of that angle. Then you get a circle. That's the way it is. So this is weight 1 is cosine, cos of alpha. Okay. So this is L, and of course this also has to be L. That's the configuration. Where's the rest of the circle? This is from 0 to 1, right? The parameterization. You remember that? They also have this t thing, right? T is running from 0 to 1, right? You use different t values and you get different points on that curve, right? Where's the rest of the circle? The rest of the circle lives here, right? How do you get that? Well, you evaluate to the left of 0 and you evaluate to the right of 1, and then you get the rest of the circle, right? All right. So now we come to the specific case of representing a quarter of a circle, okay? Or a third of a circle. These are the important cases. How do we represent just a quarter of a circle? This is an arbitrary arc length piece of a circle. And now we just come to the even more important cases, or more specialized cases, of just a quarter of a circle. How do we represent the quarter of a unit circle? Okay, a quarter of a unit circle. Quarter of a unit circle. How do we represent it? I'm very precise now. Here's my x, here's my y, x, y, and I want to represent 0, 1, this particular circular arc. Okay, let's say I wanted to go from here to there. So this is my B0, and my weight 0 has to be 1. Here is my B1, and my weight 1 will be something. And here is my control point B2, where the weight again has to be 1. Weight 2 equals 1. All right, and this means I run T between 0 and 1 in this way. So I run that way. All right. This is a unit circle, I say, so this is just 1, and this would be 1, right? So this would be 1, height. I said the weight there has to be the cosine of the angle, right? So the cosine of the angle is this thing. Here's this connector. So what is this angle here? This angle alpha. Alpha is 45 degrees, or that is pi over 360 is 2 pi. It's a quarter of pi, right? It's pi over 4, right? Alpha is 1. So that thing there is cosine. Cosine of pi over 4. What is that? What is cosine of pi over 4? Remember that? It's square root of 2 over 2. This magic number will come up in all kinds of representations of rotational creatures. Okay, that's where this comes from. If you can represent a quarter of a circle, then you can represent the entire circle by just putting it into the other quadrants, of course, right? Right? So now how do we represent the entire circle? Well, if we want to have a rotational surface, obviously we don't just want to have a quarter of a bottle, but we want to represent an entire rotational bottle, right? So the full circle, the full unit circle, okay. How do we get the full unit circle? This is one particular representation. There are multiple ways to get it. So here we have x, here we have y. And I say here is Here is a box with radius 2, 1, 1, 1, 1. And I want the unit circle, radius 1 in there. So I want to get this particular circle, circular arc, circular arc, circular arc, and circular arc. Okay. This will be a segmented curve. Okay. I start here with B0. This would be B1, B2. Okay. A first segment of a curve. This is a segmented setting, T. And I have obviously 4 segments. I can all parameterize them between 0 and 1 and 0 and 1 and so forth. And so I can start the parameterization at 0, 1, 2, 3, and 4, for example, for the 4 segments. And I have 4 corresponding curves. So this would be my B0, my B1, and my B2. And I need weights for that. Then I go on, B2, B3, B4, B3, B4. And I go on another segment, B4, B5, B6, B4, B5, B6. And I go on, B6, B7, B8, B6, B7, and the last point is the first point again, B8. So maybe you can step outside and tell them that this is a class. So we have 4 segments. And 4 corresponding domain intervals, first, second, third, and fourth. We have 9 control points. B0, B1, B2 is the first quadratic, rational quadratic piece, next rational quadratic piece, third and fourth rational quadratic piece. The important part is the choice of the weights. So here the weights, weight 0 is 1, weight 8 is 1, weight 2 is 1, weight 4 is 1, and weight 6 is 1. And all the others have the interior Bezier points for each of these arcs have to be square root 2 over 2. So weight 1 is square root 2 over 2. Weight 3 is square root 2 over 2. Weight 5 is square root 2 over 2. And weight 7 is square root 2 over 2. That's it. So now you know how to represent a circle. Essentially, now you know everything how to construct the rotational surface over here, right? You are smiling. You have done this already, right? Okay. So now this is all we need to know. This is all we need to understand for doing a rotational surface. If you see how this all relates, curve scheme, tensor products, a u direction and a v direction, and now being able to represent the circle, you should see how it all comes together. How you now can take a curve and rotate it about the z-axis, for example, right, and get the surface out of it, and how to construct even the control mesh for that. Shoot.
So if you're taking like a B-spline here, what you wanted to do was rotate it around the surface, you can make the outside, or this control, basically just the Bezier curve, and have that, and then connect them with like that.
Right. This essentially is a configuration of one of the control points for the curve that you would like to rotate. Right? The z-axis, you can think of the z-axis now as coming out of the board. Right? And this control point here, this B0 control point, is one of many control points coming out of the board for a curve that is here that you want to rotate around, right? In this way. And so if you understand how to rotate around in this way, well, this is not really a rotation of control points. This is arrangement of a bunch of control points in a square fashion, right, with proper weights. If you know how to do this, you use this configuration for all the other control point layers which are above the board. right, for the particular curve that is here that you want to rotate around, the z-axis which comes out of the board. Right? Does it make sense, the thinking? You only need to know how to represent a circle, because the rotational surface means you have one curve, you rotate it around. Everywhere on that rotational surface you have circles, right? So it's this scheme that defines it all. So we will come to that and have to understand how to do that, which will be probably two very important surfaces of revolution that you need to represent in engineering design over and over again. This one, which is what? A cylinder comes up, of course, all the time. And the other important thing is a sphere, right? So cylinders and spheres are absolutely crucial. You can even put those on the board, what the control point information is for those. And then you can store the control point information for a sphere or an octant of a sphere and a cylinder. And then when you need a cylinder, you just copy it, right? You just copy the control info for a cylinder. And you only scale it, right? You change the length and change the diameter, right? That's a higher level thinking even when we go into the software engineering of an entire system. So now we need to worry about constructing a surface of revolution. We want a surface of revolution. Surface of revolution. Revolution. What? Rotational surface, right? Rotational surface, rotational surf. You can reduce it always to rotation about the z-axis, right? In principle, of course, you want to rotate about an arbitrary axis in 3 space, but that arbitrary axis always can be mapped to the z-axis of your world coordinate system. So we really only need to understand how to rotate about the z-axis. Rotate about the z-axis. Okay, how do we do it? So this is the essential operation that we want to do. Again, first we don't worry about the control points, we just worry about the geometry and what we would like to achieve. So, say I have some kind of geometry. Right? This is it. You want to rotate it about the z-axis, say by 90 degrees. Then, of course, the same shape would appear here. And you rotate, right? And you get the idea of what's going on. So x-axis, y-axis. And what do? You specify one curve. This is the one curve that you specify. Curve, I call that u, right? So that will be your u parameter direction. So your u parameter is running that way. That means the v parameter has to be used for the rotational part, to rotate it around, right? So this rotational then is the v parameter direction. Specify one curve, rotate it about the z-axis by, 90 degrees. If you know how to do it by 90 degrees, then you can copy it into the 4 other quadrants. You also can do that. For rotational surfaces, you only need to carry around the control information for 1/4. You can save the rest, because the rest comes from copying, right? You see that. You only need the representation for 1/4 of a circle. The rest is obtained by flipping and copying over, right? You don't need that. So now we actually worry about the representation of a rotational creature. And I want to combine polynomial world and rational world. Say the particular curve that I would like to rotate around is polynomial, so I can represent that as a Bezier curve. But then as soon as I start rotating it around, the surface has to become rational because I have these circles there, right? As soon as I talk circles, I need these weights, which are different from 1. So let's look at least into one example. And I think I have just enough time to go over that. Rotational surface and I just do the Bezier, the rational Bezier case. I can also go to the rational NURBS scale, to the rational B-spline case later. Rational surface, rational Bezier surface, Bezier surface. Okay, so now we know our case can always be reduced to rotation about the z-axis. Rotation about z-axis. Z-axis. How do we do that? I put the z-axis here. I put the x-axis there. Put the y-axis there. X, y, and z. I want to rotate about this z-axis. And I only need to think in terms of the control polygon. All the operations I do in the setting of control polygons and control meshes, I only need to apply the rotational part to the control points, okay? The geometry follows the continuum. Just like with the ruled surface or extruded surface, right? I did the extrusion by just applying the extrusion vector to the control points, and the surface followed. Same for the ruling. For the ruling, I specified the control points for curve 1, the control points for curve 2, and then I just connected the control points, and that was the surface coming out as a byproduct, right? The continuum comes out. Here, forget about the curve. I just think in terms of the control points of a curve, and I will rotate these control points around, and the surface automatically will be constructed. So that's the general thinking. Let me see whether I can put a very simple control polygon here. Okay. Okay, this is a control polygon of something. Control polygon, control point, control point, control point, control point, and I want to rotate this around. No? Okay. So if I do that, then of course I get the corresponding control polygon here, rotated around by 90 degrees, right? And now you remember I needed to do this, right? If I have control point here and control point there, the other one has to be there, right? So this is a control point here, and then I rotate it around on a circle to go over there. But this control point there is, so this was some kind of L. This is some kind of L, right? And it moves on this circle, which has radius L. So that means this one has to be of length L times square root 2 over 2, right? To be on that square configuration. I need the square configuration. So that means I'm here and I need the square configuration, right? Here's a square. Here's a square. Here is a square configuration, and here's a square configuration, right? So, and then I have this and that. So, and you see these 4 layers of this configuration here, 4 times on top, right? In the z direction. So, now I can say this was my original. If I call this now the u direction, I call this guy B0. This was my B1. And this, say, is my BM. Okay. Then these will be the corresponding points. Well, okay, so this was for the curve, right? Then I can already say that this is B0, 0, this is B1, 0, and this is BM, 0. Right? These are then the second point, so this must be B02, this is B12, and this one must be BM2, right? And I need to understand how to get these guys. This is a B01, and this is a B11, and so forth, right? And this will be the V parameter direction. U goes down like this, V goes around. Okay, so what do I have? What does the user specify? The user specifies only the control points for the curve that is to be rotated, right? This is a curve that he, she has specified. So this is a curve, right, that exists here, and this curve will be rotated around to produce that ending curve there, right? Then anywhere in between, it will be the rotational surface, right? Or you need to understand how to take a particular BI0 and from a BI0 construct the BI1 and the BI2 with the corresponding weights, right? So the surface is entirely specified by the user, who specifies the curve. User specifies this particular curve, C of u, which is some type of Bezier curve, just polynomial. I don't even make that rational. I from 0 to m of Bezier points bi times bim of u. Okay, that's what comes in as input. And now I need to represent this quarter surface of revolution with bij control points. So I need the surface of uv has to be a rational creature. It has to be rational. It's a rational Bezier surface. So I need this expression. It is a sum, and divide by a sum and sum. What has to go there? Well, the I runs from 0 to m. That's a curve. I from 0 to m. I from 0 to m. And j, how many control points do I have in the v direction? 1, 2, 3, so it goes from 0 to 2. J from 0 to 2. J goes from 0 to 2. J goes from 0 to 2. I need to worry about the weights. There are weights for all these control points, right? We have to acknowledge that. There are weights now. Weight ij times the Bezier points bij times Bernstein polynomials im of u and bj, well, they are quadratics, right? bj2 of v, circles, quadratics. So divided by the weights, wij times Bernstein polynomial im of u times bj2 of v. Okay, we need to understand two things, and two things only. How do we get the weights and the control points from the information that I have on my guiding curve that I rotate around? That's the only thing I need to understand. Okay, and if I understand it for one of these layers in the z direction, then I understand it for all the layers, of course. So the last thing I really have to put on the board is to say how this for a specific I, for some specific index I. Okay. What do we have? This is the situation. I have my z-axis. I have one particular beast like that. So here is my x direction, here is my y direction. Y, x. This is my z-axis about which I rotate. And here is one particular point. This is a original bi value of this curve that I've specified. This one will be another point and another point. See, I specify my curve I want to rotate, I specify in this plane y equals 0. Oh, that's the plane where I specify everything. And then rotate this around. Okay, what do I have to do here? This bi becomes my bi0, and that's the beginning of the surface of revolution. So here is that curve, so that the weight there, weight I0 is 1. Okay. I take this point and I rotate it around about the z-axis by 90 degrees to end up at that point. So this is B I2, which also will have a weight I2, which is also 1. Okay, here weight I0 is 1. Only need to worry about the location of this point. This point lies at the same height, the same z. Okay, and so there is a certain distance here, a certain distance L. And this one has to be L, right? And this is L. And you know how to compute that length of L. Huh? And I need the weight for this guy. So this is point BI, 1. And it has a weight I, 1, which is square root 2 over 2. Okay, we talked about that. That is square root 2 over 2 for us to be able to represent the circular arc on this much larger surface of revolution. Okay. So where I can say now here where weight I, 0 equals weight I, 2 equals 1, and all the interior weights, weight I, 1, equals square root 2 over 2. That's the condition for the weights. All right, and the interior Bezier points, this interior Bezier point is just taking this point here in the y equals 0 plane and translating it by a vector that is given by the unit vector along the y-axis, translating it by this unit vector on the y-axis by the length of L to get to this point. And this point, of course, is the original point obtained via a 90-degree rotation about C, and that's it. And you do this for all the layers of the entire curve that lives here, right? And then you rotate all of that around, and you get a rotational shape. So it's always the same operation for all the control points, for all the weights. And I look forward to your presentations next week. Thank you.
The preceding program was brought to you by UC Davis on iTunes U. Please visit us at itunes.ucdavis.edu.